Good afternoon, everybody, or good evening, whenever you are watching. Today is the day of Digit DP Part 2. Yesterday, we were solving a problem on which I was stuck. So, this was the problem number of beautiful integers in a range. So, we were discussing about how to take care of heights, tight, how to take care of leading zeros, or maybe maintain some other characteristics like number of ones, appearance of a particular digit, some other things, keeping track, how many zeros, similar things. This problem, we have to take care of divisibility by a number. That's makes this problem interesting. Why? Imagine that I have a digit that I put in a particular position. Then I put the next digit. How will I keep track that if I add this digit or append this digit, the new number that is formed, if it is divisible by the origin, and if it is divisible by particular k that is given in the question, what happens if I add more? It is not possible for us to make the entire digit, make the entire number and check divisibility, because the size of the number can be up to 10 to the power 9, and when we are dealing with digit dp, we can deal up to 10 to the power 10 to the power 5. So even though this problem is simpler compared to that, like it is only asking for low high up to 10 to the power 9, still we have to keep track of digits as we put. So it's like, let's go back. Mhm. So imagine, so we have, let's say we start putting in digits. And one important thing to observe is that k is up to 20. So maybe this gives us a little bit of hint. Let's say I put a digit 2 here. And let's say the value of k is 5. So what is 2 modulo 5? 2. What if I put a 1 here? We have to propagate our previous answer to the next stage. Like if the number becomes from 2 to 21, how does my answer get affected, and how it is getting updated, and if we can carry some value up to the end, maybe that can help us. Okay, so we will use some properties of modulus. Imagine I have, let's say, okay, we will use some properties. Let me just mention the properties that we will use. That a plus b this property of distribution of moduli, we'll use this also. We will use this as well. So these are the two properties we will use, but how? So given the value of k, we will keep track of the modulo. Initially the number is 0, we have not formed anything, and we put in digit, and that digit modulo 5 we calculate, and initially we say 0 is what we came with. So let's say k is 5 and I came with a 0. My first digit, let's say I put 2. I can write this 2 as 0 into 10 plus 2. It's like if I have a modulus that gets shifted, 2 gets appended, that thing, modulo 5. is 2. Now 2 modulo 5 I know, and I carry forward to the next step. Let's say I put a digit called 3. Now I know that up to 2 modulo 5 is 2. The new number that is formed is 2 times the previous number. Like I should say, like 2 times 10 plus 3. And I want to calculate modulo 5 of this. So if I came with 2, I multiply it with 10, add 3, modulo 5 we calculate, we get it is 3. And that is indeed 23 modulo 5 is 3. So what we will do now? We will treat 23 as 3. Why can we do this? Because imagine if I put something else like 4 here. Now 2, 3, 4 and 3, 4 with respect to modulo 5 is same. Of course, both of them are 4. Now 5 may look very special. Let's try it with something else that is not very nice, like 7. Initially I start with a 2. 2 modulo 7 is 2. Then 23 came. So 23 modulo 7 is 2. So I came with a 2. So I came with a 2 here. Now my claim is 234 and 24 modulo 7 will be same. Let's check. 24 modulo 7 is 3 and 234 modulo 7. Imagine 234 na. If I decide to divide 230, it's like 223 into 10 modulo 7 plus 4 modulo 7. Like, so 23, my claim is 23 modulo 7 and 2 modulo 7 is same. That is obvious because 23 modulo 7 is 7. Now I am shifting. I have claimed that 234 can be written as 23 into 10 plus 4 modulo 7. And 24 is 2 into 10 plus 4 modulo 7. But from the previous step, we have calculated that 23 modulo 7 is 2. So either I do, and we have proved that this modulus is distributive. So 23 modulo 7 I can write as 2 modulo 7. That's why this is applicable. We can check for any other number as well. So we have proved it for the general case, like any number modulo anything, we can carry forward the modulus, and by using the distributive property we can prove that we don't need to take care of the entire big digits, just modulo that k carrying that is sufficient. It's like, let's say I have a number a b c d e. So e I am putting first is d e modulo k, and that's what we are doing, or we are doing d into 10 plus e modulo k we are doing, or in other case we are saying that a plus a b c d e modulo k, and we know that a b c d, mm, let's make it p. We know that this is p. So a b c d modulo k is p. That is what we are carrying forward up to e, and we are doing pe modulo k, and we want to show that both of this results to the same answer. Okay, so let's say it will be a into 10 to the power 3 plus b into 10 to the power 2 plus c into 10 square, c into 10 plus d modulo k, and we know that this is p. Okay, so we want to say that modulo this is k, so we want to just do it for the next step. It's not it is not, so we were trying to do it inductively. We don't need to consider all these three numbers. Even though it can be proven for all these numbers as well, but we already know, let's say, let's consider an intermediate step. We know that a modulo k is b, what we have carried forward. Let's call it a1. ab modulo k is a2. abc modulo k is a3. abcd modulo k is a4, right? And we are doing a4 modulo e, like a4e into 10 plus e modulo k we are doing, right? This is what we are doing after carrying the modulo. My claim is that this will result to the same thing as the entire thing. So that is a b c d e modulo k, right? So how can we prove this? We have all these equations available to us, right? So let's do. This is a into 10 to the power 4 plus b into 10 to the power 3 plus c into 10 to the power 2 plus d into 10 square into 10 plus e modulo k. Now we know that a modulo k is k a1. So a1 into 10 to the power 4 mod k plus b1 into 10 to the power 3 mod k plus, I mean, this should be a2 plus a3 then square. C is a3 now. No, we have said that ABCD modulo k. Yeah, ABCD modulo k is, so this will ABCD as in number, no? So can I say that if I take 10 common out of here, I will get ABCD as a number, and plus E we can do. And we know that ABCD modulo k is A1, no? A4. So this is 10 into A4 plus E modulo k. So equal to 10 into a4 plus e modulo k. So proven through induction. So we have assumed up to ABCD and we have proven from ABCD to E, right? So this is the inductive step. So we will use this and we will carry forward only up to necessary and we will multiply it by 10 and make space. So that's how we will solve this problem. We just had to prove that the entire number generation is not important. We can just carry the modulo up to that. Okay. Just give me a moment. Yeah, it should be there. So this is the problem that we were solving. We were trying to solve. So number of beautiful integers in the range. We'll use the same ideas. So again, we will use the prefix sum idea because it is saying from low to high. So we will do from 0 to low minus 1 and 0 to high, and we will subtract. So let's make our function. Auto. Let me just increase the fan speed a little bit. Okay. Okay. So the name of the function can be anything. We call it deep recurrence. We do have an index. We can have a leading zero. We can have a int tight. I think Boolean tight. If it is a leading zero, leading zero, and I think we will require the running mod. So let's call it RM. And since k is up to 20, running mod can be up to 19. Do I require anything else? Probably not. So we will calculate int lower bound is 0 and int upper bound will be depending upon tight. So if tight, then we will say that okay, and of course we have to carry the string as well on string s, which we will carry through reference. So if it is tight, then we say that s of idx minus 0. Otherwise, we just set it to 9 and we just loop lower bound. So this is what we put as the current digit. Now initially we came with a value of running modulo. So int new modulo equal to 10 into running modulo. Of course, you have to carry the k as well. Of course, k is constant, so we don't have to worry. 10 into running modulo plus this I that I'm putting modulo my k. And we will just pass. Let's pass. So and we can do but I think I will have a return type as well. So let's say int result equal to 0, and of course we in the end we will return if it is divisible. If idx equal to size of, I should say, s dot size, then we can just return rm equal to 1. I mean, if it is 0, then we return 1, otherwise we return 0. So self idx will be idx plus 1. Tight will be dependent on if I am already tight, and this I that I'm sending is equal to this upper bound, right? If I is the upper bound, then it is tight again. Leading 0 is dependent on if I'm already leading, and if I is still 0. Running mod is the new mod, and S remains as it is. So result plus equal to. Yes, this should be sufficient. So let's check. So let's say int r equal to recurrence. Index is 0, tight is initially 1, leading 0 is initially, is it leading 0? Yes, it is leading 0. Running mod is 0. String is toString of, I think, high. And int L is the same thing, but it's just toString. This is low -1. And we return this R minus L. Let's see, we probably have some simple errors to solve. Type that has been sent to us returns a constant value. Okay, this is equal to per bound. Oh, this would be minus, not equal to. Okay. Okay, this will be a semicolon. Okay, there will be a semicolon here as well. Okay, so let's see. So my output is 10. If it is divisible by k. Yeah, running mode is 0. Index starts from 0, tight is initially 1. Leading 0, we don't have to care about much. Output is 3. Expected is 2. Between 10 and 20. Let's try to print the value of L and R. So 7. So between 0 and 20, there are 7 integers that are divisible by 3. So 3 zeros is 0. Well, low cannot be 1, can it? No. Am I counting 0? Anyways, does not matter. So 0, 3, 6, 9, 12, 15, 18. So 7. And it is 7. And between 10, it is 0, 3, 6, 9, 4. 7 minus 4, it is 3. But the expected answer is 2. Uh, okay. I think I'm correct in some aspects. So it's like up to 20. We have 0, 3, 6, 9, 12, 15, 18. And up to 10, we have 0, 3, 6, 9. So 3 are left. Question is it considering this 12 and 18? Why not 15? Okay, the count of even digits is equal to the number of odd digits. Okay, then we have to maintain 2 more variables. Okay, I actually did not read the first condition. So let's include that. So I int ed and I think is equal to od na. So ed minus od, edm od. Okay, we will maintain this as well. And this is very simple. Before sending in s, we will just say edmod minus even minus odd na. So okay, we can just say that edmod no, not here, do it here, edmod plus equal to if I modulo 2 equal to 0 and minus equal to, so this kind of keep tracks, and edmod equal to 0, right? And we will send this and we can just keep track of this edmod thingy. Okay, I have to consider that as well. Initially it's 0 and initially this is also 0. Okay, even minus odd. It is 1 in what case? Number of even digits. So if it is even, Should I keep track of this separately? I don't think so. Because I just have to check if they're equal or not. We can just do simply if I modulo 2 equal to 0, then ed mod is equal to 1, else ed mod minus equal to 1. Does it solve our problem? No, it's the same thing. But I think after the next iteration, na, before going to the next iteration, I think I should uh, revert it back. Yeah, because we are using the same variable. In every other case, we were doing something else. Still not good. 4 and a 0. Okay, a little bit different. Let's make a new variable. Of course, we will take care of that as well. So let's say int n edmod equal to edmod, and if ne if I modulo 2 to 0 nedmod plus plus, else edmod minus minus, I mean nedmod, of course. Then we can just send in the one with the n. Of course, this will probably lead to the same result as 4 and 0, but I want to count how is it 4 and 0. Like 4 as in number of even digits and number of odd digits. Of course, one thing we have to consider that we cannot have leading zeros, can we? Cannot count leading zeros. So if LZ equal to and I equal to 0, then continue. Because that will mess up my calculation, will it not? Yeah, that was messing up my calculation. Let's see if this is passed. This probably this will give time limit exceeded because we did not memoize at all. Okay, so 47 and 100, k is 18. Hmm. Let's think. Divisibility by 18. The thing that I was checking will probably work for one digit numbers. Or it should work for two digit numbers as well. So we got 0 for the first one. Why? So if we go back to, okay, it was not visible. This is the code that I have written up to. We have to come back to iPad. So 18 divisibility. So 0, 18, 36, 54, and 18 fours, 18, 82, 36, 18, 54, 18 fours are 76, 18 fives are 90. That is 1 plus, so 1, 2, 3, 4, 5, 6. Yeah, 18 fours are 76. 40 plus 8 fours are 36. No, 8 fours are 72. That's an issue. So we have 5. And up to 47, I think only these 3. So the answer should be 3. Why is it giving 0? Of course, you have to count the number of even digits and odd digits as well. So even odd, even odd, even odd, even odd, even odd. So all are good. 0 we don't have to consider. So let's say R is like S is 100. Right? No. If it is leading 0, we cannot continue. We will just not consider that in our EDMOD calculation. So yeah, we will not, but we will still we will put zeros. So we can do like, then we can just keep n else. So it's like if it is 0, then we will just consider the old value that I came with. Otherwise, we will consider that into our calculation. Let's use this test case. because we cannot just continue, can we? Now we will just memoize. So since it's a lambda function, so we can just do it here in dp. So first is idx. I think 10 is sufficient. Tight 2, leading 0 also 2. Modulo can be up to 0 to 19, so 20 is sufficient. And ED maximum, if all of them are even, so 10 from 0. So if TP of this entire thing ITX tight LZ memset TP minus 1. Okay, let's run it now. Okay, out of bounds. Minus 1. Where is it keeping minus 1? Index tight leading 0, running modulo. Can modulo be minus 1? EDMOD can be minus 1, right? What if odd digits comes first? Then it can be minus 1. So let's memoize it like EDMOD plus 20. And let's make it up to 40. Let's do 41 first for being safe. Yeah. Do I require 41 or 40 is sufficient? We will think about that. Yeah, it's accepted. Let's see. So minus 19 is possible. No, minus 9 is possible. So it's like my range is from minus 9, like all of them are odd, 10 to the power 9. So 1 followed by 9 digits. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now all of these are, let's say, so the maximum number possible is 1, 2, 3, 4, 5, 6, 7, 8, 9. So minus 9 is the minimum number. Can it be minus 10? 10 odd numbers. Not possible. And maximum can be, I think, all of them are even numbers. So this only, let's say 9. So if I do just plus 9 to everything, so it will go from 0 to 18. So up to 19 is sufficient. Yep. Plus 9, let's do. And plus, I think, plus 18 is sufficient. 0 to 18, so 19 should be sufficient. Let's try to run. Let's try to sum. Like we are really playing on the bounds. I'm thinking, can this be hacked? Let's think. What if all my digits are 9? The worst case. Like the lower bound and the upper bound are very close to each other. So that only one digit with all the digits to be 9. Yeah, we can keep some bounds loose. But if it is up to 10 to the power 9, then maximum 10 digits possible. But 10 digit number is only one, the 10 to the power 9% itself. And that digit does not have, what should I say, 10 in terms of difference in each, like 10 odds and no evens. That is not the case. And the minimum number is 0. So this is sufficient, right? I hope you understood this problem. Uh, the while I was writing the first part of this code, this iPad was screen was actually on, but we have followed the exact same conventions that we have followed in our previous class. That there is an index, there is a tight, there is a leading 0. The only difference is we carried the running modulo, and this thing, this new modulo is 10 into running modulo plus I modulo k. And we have proved that this is same as taking the entire block that we have left behind. That will be all for today. Let's see if we have some extra questions that we have not solved the previous day. Otherwise, let this be the problem of today. Okay, we have spent a lot of time in this problem, but I guess it will be worth it. Thank you very much for watching. If we find any other good problems in DigitDP, I will continue the series with that problem. Otherwise, the 5 or 6 problems we have solved will cover most standard questions that are asked from DigitDP. Thank you very much for watching. Have a great day.